Good morning, everybody. Today we're going to be reviewing in session 3 overpressure control to prevent pressure from building up inside the shelter. Usually if you're in a shelter that is designed to be a bomb shelter, that's not a fallout shelter, but designed to be exposed to either blast wave or overpressure or ground shock, then you would be in this category requiring some type of overpressure control inside the shelter. This is a blast wave here. When the air comes down inside the shelter, there should be some type of control here to prevent pressure from building up inside the shelter. That's called overpressure control. What we're trying to do with overpressure control is prevent the pressure from getting above 10 psi inside the shelter. That's usually the pretty standard limit. And this is pressure that occurs instantaneously. Consider a man diving off a diving board and he goes 10 feet below the surface of the water. That's 10 feet which is instantaneously. He's going to experience 4.4 psi of pressure on his lungs and his eardrums. If he goes 20 feet deep, he's going to expose 8.8 psi on his lungs, his eardrums, instantaneously. So just to give you a reference point, those kind of pressures we do deal with normally. But again, 10 psi is about the limit, because what happens inside a shelter is not instantaneously. It's over a couple seconds. So we're talking about pressure from overpressure, which forces air in the inlet and forces air in the air outlet, building up pressure inside this shelter. And consider this. This is the difference between overpressure and blast wave. This is a dam. This is a man at the bottom of the dam. He's experiencing overpressure, but he's not moving. If you push the dam over, the dam fails, falls over. Now he's got overpressure and he's moving. He's got this blast wave blowing him across. So over here we have crush, over here we have blow away. It's an important concept because it affects how you design your air manifolds and how you deal with your overpressure control. In this slide, we've got a mushroom air manifold connected to a radiation bend, connected to a blast valve. This is the usual placement for a blast valve. And when you put it here, or even farther away, it can also be exposed to reflected overpressure. In some of the shelters that I've designed, this blast valve might be 40 feet away. In that case, it actually gets more pressure because you end up with what's called a reflected overpressure or hammer. So this is usually where you put it in. You would not need this for something that's designed as a fallout shelter. A typical blast valve functions like this. If the overpressure comes down here, this wafer plate seals against here and stops that sudden burst of pressure. It also works for the negative part. There's a negative part of this. As the blast wave passes, there's some suction, and this comes up and seals against here. So that's how a blast wave works. They should be stainless steel or aluminum. They are subject to rust because they're connected to an air manifold which draws moisture down. The duration of the blast is very short. Even for 100 psi, it's barely a second. You go down to 20 psi. This is 2.5 psi here. I mean, it's just basically a second, so it's very quick. You can see it in table form here. We originally started our shelter designing it for 1 atmosphere. So here's 15 psi at 0.7 for 100 kiloton surface burst. So here's our blast wind, 400 miles an hour. So if you're designing a shelter, a rated shelter, you've got to withstand this overpressure, and you have to withstand on the air manifolds and the hatch, you have to withstand 400 miles per hour. And keep in mind that in that 400 miles per hour, you're going to have flying debris in that. So there's going to be a 10, 15, 20, maybe a 50-pound something flying in the air that can hit that air manifold. So it has to be able to resist that flying debris. The other way to do it is not use a blast valve and use overpressure choking. Overpressure choking has no moving parts. It simply sizes this air inlet and this air outlet. So in that 1 second, you can't get enough air into the shelter to pressurize it. Consider holding a 1 liter soda bottle. You can shake it up, turn it upside down, pull the cap off. All that soda inside that bottle can't come out. Even under all that pressure, it can't come out. It's still going to take a couple seconds. And after a couple seconds, the blast wave is over. The overpressure is over. So what you can do, and there's other examples in the book. We used a 500 kiloton surface burst for this. A duct length on the outlet of 10 feet, a duct length on the inlet of 10 feet, at 20 psi overpressure, which happens to be 1 mile from ground zero for a 500 kiloton surface burst. But if your shelter has, for example, 4,000 cubic feet in it, and you're using a 6-inch air inlet and a 6-inch air outlet, you're going to get 2.4 psi pressure maximum inside the shelter. That's assuming that the weapon detonates properly, assuming that the land is flat, assuming that there's no buildings to obstruct the blast wave. So this is the most that you're going to get inside the shelter. Anything above 10 psi is shaded in yellow. So these are not acceptable in yellow here. But all these others, as the shelter gets bigger, the pressure goes down because the relationship of the diameter of the air inlet and outlet to the volume is a different ratio. If you have pipes, and the thing about overpressure choking, there's no mechanism to fail. With blast valves, I've had mice build nests in it, which would hinder it from closing. There's some corrosion issues, so the blast valve should always be stainless steel or aluminum, and you can get all kinds of insects building nests in there. So that's only if you fail to put a screen on the air inlet on the air manifold. So you can avoid some of that or all of that if you overpressure choke it. There's nothing to fail. There's no mechanism. If you have an air inlet and outlet on an existing shelter that's too big, that would put the shelter down in this overpressure range, you can go to a choke plate, and that's simply a ring where you limit the diameter here to the size that you need to reduce the overpressure inside the shelter. It's a simple approach. There are other tables in POP that'll show you different overpressures, and you can, if you have larger shelters, you can use that on a linear basis and expand that.